Okay, so we're gonna kind of pick up where we left off in class today. This is the next page over from where we're working today. I believe it is page 243, if I'm not mistaken, or somewhere over there. Okay, so we talked about parametric equations, and we're gonna kind of talk about vector equations as well, because vector equations are just a special type of parametric equation. So I know in physics you guys use this notation. So like for a velocity vector, you use this. Something that looks like that. In calculus, we use this notation where we have an x component and a y component of this vector. And of course, this is graphically, we're talking about vectors on an actual graph. We're not just talking about, we won't go too far into vectors like the way you guys do in physics. But kind of just want to get some basic information, like when we talked about regular functions and we talked about motion, we talked about motion along a straight line. So we're always thinking about motion going towards the origin or going towards the point of start or away from the point of your initial value. But with vectors, we actually, because of the fact that they are parametric, we can actually go more in depth. So our movement is no longer just horizontal movement. Our movement is going to be horizontal and vertical at the same time. Okay, which is, if we actually were to graph that kind of movement, we get that parametric equation like we talked about yesterday. Okay, so when we talk about vectors, we're talking about motion on a coordinate grid. So our position vector is just really our x of t and our y sub t, very much like a parametric equation. From basic derivatives, we know that if we take the derivative of position, we get velocity, and that's true even here. So our velocity vector is really just the derivative of our position vector. So x prime of t and y prime of t. Okay, so we have that third variable, that independent variable of t now. Okay, and when we're talking about motion, our t is going to represent time. Okay, our acceleration vector, we know if we take the second derivative, we get the acceleration vector, and that's still true here. So our acceleration is just the second derivative of position, or the first derivative of velocity. Same thing here. So our acceleration vector. Now, our distance traveled, because we're on a parametric curve, even though we're talking about vectors, the fact that we're on a parametric curve, our distance travel is actually going to be the length of the curve that we kind of traveled on, which means for distance traveled, we can go back to the idea of the arc length itself. So our distance traveled in parametric form or in vector form is that same formula that we use for arc length. So a to b integral of x prime of t squared and y prime of t squared with respect to t. Now our speed formula in vector, because speed is actually the distance between your velocity vectors. So we go back to the idea of using our velocity to calculate speed. We know velocity is just the absolute value, or the absolute value of velocity is speed. But in vector form, that distance is actually, that speed is actually the distance. So we use a distance formula to actually figure out speed when we're in vector form. So that distance formula goes back to that same thing. We're still using our velocity, and we're using our distance formula here. And we get that. Very close. So these two values right here, or these two equations, are very close to each other. So these two right here, very close to each other, where speed doesn't have the antiderivative or the integral, and distance does. But if we think about distance, distance is just the accumulation of your speed. So it makes sense that we would take our speed equation and integrate it to get that accumulation. So distance is the accumulation of speed. Distance is the accumulation of speed. Distance, one more time, is the accumulation of speed. So we kind of want to write that down since I've said it 3 times. Okay, so example, it says a particle moves in the xy plane so that any time t, the position of the particle is given by x of t and y sub t. Find the velocity vector. So x of t and y sub t are going to represent our position. So to get our velocity vector, all we have to do is take the derivative of each of those components. So our velocity vector itself would be equal to taking the derivative, so 3t squared minus 8t. That's going to be our x component of our velocity vector. And then our y component would be 4t cubed plus 6t squared, and just the derivative. So that gives us our velocity vector. Now to get the actual velocity vector when t is equal to 1, all we're going to do is take our velocity and plug in, sorry, not a t, but we're going to plug in a 1 for that t. That looks very messy. So plugging in a 1. So for every t value in here, we're just going to plug in a 1. That's going to give us our x component. If we plug in a 1, sorry, I caught the bell. That's going to give us our y component. Okay, and then if we calculate that, that's just going to give us 3 minus 8, which is -5. So -5. And then 4 plus 6 will give us a positive 10. Okay, and all we're doing is calculating that. So this is our velocity vector. So that means, because this is negative, our x value represents how we're moving left and right on this plane. So we're actually moving left right now because our value is negative. The y component tells us how we're moving up and down. Because it's positive, we're moving up. So now we can get a clearer picture of what this movement looks like. So what I want you to do after watching this video is just do B and C. Leave D for in class because D is a more complicated part. But B and C you guys can manage. Okay, so if you have questions, come and see me.